All right, so we're gonna probably do this over a day or two, maybe even three. We'll kind of see, but we're gonna be talking about related rates. Now, related rates is one of the more challenging sections in calculus. It's not because the work is extremely difficult, but it's because they're word problems, and people don't like word problems, so they always feel like word problems are impossible. So what should I do, right? So we're going to be working with word problems and try to help you understand the wording in it and how the words themselves tell you what you need to do. Like a word problem in calculus a lot of times is basically just an answer key. The way they express things, the way they say things, tells you do this, do that, do that. But you have to be able to identify it, right? So you have to know the terminology, the words they might use to mean certain things. So that's kind of the hard part to related rates. It's not so much the work, because the work is still just going to be derivatives implicitly. We're going to be doing implicit differentiation a lot. So that's not going to be like supposedly the hard part of it. The hard part is just you trying to translate things properly so that you can write the correct equations. Now, for the most part, the equations will be simple in terms of shapes. They're usually shapes, geometric shapes. That's the reason why I gave you guys that big old printout, and I think it's the second page, has a bunch of geometric equations, right? So that you guys can remember, like, what is a cylinder, what's a triangular prism, stuff like that, okay? They're not going to maybe tell you to use a triangular prism, but they might say, okay, on a conveyor belt, sand is falling down on the ground at a certain rate. Well, if you think about it, if you're dropping sand on the ground, it's going to start to pile up, right? And it's going to look triangular. So you're going to think, okay, three-dimensional triangle, triangular prism, right? That's what you got to kind of start working with. But overall, I mean, just to kind of explain what a related rate is, it's when a variable changes with respect to time. So we're going to put that right here. When variables change with respect to time. So in other words, unless they state otherwise, most of your problems will be like dx dt, dy dt, dA dt, like for area, dA dt, dV dt if you're doing volume, right? Everything's going to tend to be based on time, okay? So everything's going to be done with respect to time. So the dt on the bottom, okay? So that's one of the big things you have to be aware of. So let's kind of think about this really quick. Water is pouring out. I mean, you can call this example 1 if you want. I'm not labeling it. I'm just going to kind of give you a little look into this. So water is pouring out of a conical tank. So conical tank, so a cone, where V, R, and H are all functions of time. So in other words, they all have a relationship with time. Okay, so that means I can take a derivative of them with respect to time because they're all functions of time. Okay, so we're going to assume V, R, and H are functions of time. Okay, now the equation for a conical tank is V equal to, now remember this is a cone, so it's going to be pi over 3 R squared H. Now, if I were to ask you to take a derivative of this with respect to time, so we can see how volume changes over time, how the height will change over time, how the radius changes over time, we can take a derivative implicitly. Okay? So let's do that. Let's take implicit differentiation of this whole thing with respect to time, okay, with dt is on the bottom. So when I take a derivative of volume, what do I get? Just again, big V is just a variable. What should I get? 1, right? So this is going to be 1 dV dt. Notice, because I took a derivative of v when I should have taken derivatives of t, right? Now, the pi over 3 is a constant, but you should note that the r squared h is going to be a product rule, right? Because they're saying r and h are functions. So I got to do that using a product rule. So the derivative of r squared is 2r dr dt h. That's the first part, okay? The derivative of r squared times h, so 2r dr dt h plus r squared, and the derivative of h is 1 dh dt. So if I kind of just rewrite this just to clean it up a bit, dv dt is equal to pi over 3 times 2rh dr dt plus r squared dh dt. And what I have here is I have a function that relates how the radius will change over time, right? This right here tells me how the radius is going to change over time. If I wanted to figure that out, I just solve for dr dt. If I wanted to figure out how does the height change for this conical tank over time, well, that's right here, dh dt. If I wanted to know how does the volume change over time, well, that's finding out dv dt. So right now this equation is set up to figure out how the volume is going to change over time. All I need to know is the radius, the height, the rate at which the radius is changing at, and the rate at which the height is changing at. And if you're wondering, well, how am I going to figure that out? They usually give you enough information. Okay, they'll usually tell you that the radius is changing at a constant rate of 5 meters per second or something like that. And the height is changing at a specific rate of the following, okay? They'll usually give you everything you need, and there's only going to be like one thing you don't know, and that's the one thing you need to solve for, okay? But this is kind of what these problems are going to look like. They're going to start out with some kind of word problem. So right here we started off with water is pouring out of a conical tank. The fact that they're saying something is occurring to it means that this tank, the volume of it is changing over time because it's getting empty, right? It's getting empty. So the volume of it is going to be changing every second, right? So if you can't see what they're basically saying, so just think of it like a leak, right? So you have water, right? But then right now the water will start up here. But as this thing starts to leak, it's going to eventually end up down here and down here and down here. And every second that the water keeps going down, our volume is changing, right? The volume is changing. The height of the water is changing. The radius is getting smaller as it reaches the bottom of the cone, right? All these things are changing as time goes on. So volume is changing, dv dt. Radius is changing, dr dt. The height is changing, dh dt. Okay, all of that is moving with time. As time goes on, things are changing. And they change every instant. Every half second, I got a new radius, a new height, and a new volume. Every millisecond, I have a new radius, a new height, and a new volume. Okay? So this is why these problems confuse people, because they're like, well, what do you mean respect to time and things are changing? You have to think about it in the form that you can't just use one equation and that one equation will tell you the answers to every single possible scenario, because sometimes certain scenarios change the equations themselves as time goes on. Okay? Volume, rates, and heights, they all can change over time. Sometimes things stay steady. Think about this. What if I told you that I got a perfectly shaped soda can, okay, without none of the grooves or anything on the inside, and I punctured a hole in it at the bottom, okay? So your water's, or not water, but whatever, soda's in here. And after a couple seconds it's here, a couple more seconds it's here, right? Etc., etc. So down here there's a leak. Volume is going to change over time, right? dV dt. The height is going to change over time, right? Does the radius ever change over time? No, because the shape isn't changing in terms of its circular shape. The volume has it, because notice the volume gets thinner as it gets to the bottom. Sorry, the conical tank gets thinner as you get to the bottom. But a shape like a cylinder, the radius doesn't change. The radius actually stays constant. Okay? Different shapes will create different equations that we get to use, right? We're still going to start with the normal equation for a cylinder, right? Pi r squared h. But we're going to have to think about, like, okay, what else is changing besides just height, radius, volume, stuff like that. So that's what these problems are kind of going to look like. Now, sometimes the problems we do are not going to just be based on three-dimensional shapes. Sometimes they're going to say, okay, there's a point on a graph here, there's a point on a graph here, they're both moving towards each other. How fast are they moving towards each other, right? Or maybe we have like a parabola with a focus, and they say this point right here is moving along the curve, right? How fast is it approaching that point as it moves along the curve, right? So that's going to be distance, so you're trying to find the rate of change of the distance, right? So there's a lot of different type of things. So I'll give you an example of one of these, okay? And then that's where we're going to stop for today. So let me give you an example of one of these problems. So example number 1. Suppose x and y are differentiable functions of t and are related to y equal to x squared plus 3. Now these are some of the easier related rate problems, okay? The harder ones always tend to have like stories behind, planes taking off, stuff like that. And not that they're that much more difficult. Every picture can be redrawn as a shape. That's the most important thing. You guys have to be able to figure out shapes and stuff like that. So that's what it's related to. Find dy dt when x equals 1, given that dx dt is equal to 2 when x equals 1. So they're saying, look, you're going to take a derivative of this function with respect to time. When you take a derivative of this function with respect to time, you're going to take a derivative of y. When you do the derivative of y, you're going to have dy dt. That means that y is changing at a specific rate, dy dt. That's what they want me to find. Find dy dt when x equals 1. But they say, but if you're going to find dy dt, you're going to take a derivative of everything. There happens to be another variable there, an x. When you take the derivative of x squared, you're going to get 2x dx dt. What is dx dt? Well, that's the rate at which x is changing with respect to time. Okay, but what is its value? They're giving it to us. It's changing at a rate of 2. They didn't give us any units, just 2. Okay? When x equals to 1, the rate of change of dx dt is 2. Okay? So they're saying find dy dt. All right. So here's what I know. I gotta find dy dt. Let me use it just red here so it's a little more obvious. Dy dt when x equals 1. Okay? That's what I need to figure out. But I know that dx dt when x equals 1 is 2. So all I'm going to do is take my derivative and plug in my information. So, if y is x squared plus 3, then dy dt is equal to what? 2x, dx dt plus 0, so that's fine, right? Notice I just found dy dt. That's exactly what they wanted me to find, but they said find it when x is 1. So dy dt when x equals to 1 is 2 times 1 times 2. Okay, how did I get 2 times 1 times 2? Well, the 1 comes from the x value of 1. The 2 came from the fact that they wanted me to find dx dt when x equals 1. And they told me, and I kind of put it right here, that dx dt when x equals 1 is 2. So I was able to plug it in right there. And then just simplify, so your answer is 4. And that's it. Now, you might say, why do people hate this so much? Because they get harder. Okay? Like I said, this is kind of on the easier side. Okay? But it doesn't defeat its purpose. Variables are changing with respect to time. Okay? So, we were asked to find one of them. They gave us information about the other one. And using that information and using a derivative, I was able to figure out the solution, right? Like I said, there are different things that could occur, right? But for now, we'll just kind of stop there. I don't want to go any further. We'll dive into some stuff with area tomorrow and things. Oh, not tomorrow, but Monday.